Okay, so this week will be our last week of new material. Okay, we're going to focus on sections 11.1, 11.2, and 11.3. We're going to split 11.2 into 2 days because there's kind of a lot of stuff with that one. And if you're watching this in period 1 to 2, okay, section 11.3 we won't get to in class, but there will be a video online from this year, and there's already one from last year. Okay, if you're watching this from 5-6, we'll be doing 11.3 on Thursday. All right, so first thing we're going to look at in section 11.1 is what's called a sequence. So basically a sequence is just a list of numbers that has a pattern to it. Okay, in order to have a specific sequence, okay, there has to be some kind of formula for the sequence. So I can't just pick numbers randomly and write them down. There's got to be a method or a pattern to how I'm generating these numbers. Generally, when we want to describe a sequence, we use a lowercase letter. Just an English letter, not usually Greek letters. And the sequence I'm about to show you is called sequence B. That's what I called it. And that's the sequence. So this B with a subscript 1, B sub 2, B sub 3, all the way up to B sub n, that indicates a specific term in the sequence. So B sub 2 is 1/2. That means the second term in sequence B. B sub n means the nth term in sequence B. Now, this particular sequence is what we call finite. Okay, I'm going to write that down in a little bit. But it's finite because it ends. How do I know it ends? There's no ... on the end. If there's a ... on the end, that means that it keeps going forever. This one stops. Maybe B sub 1,000 is the last term, or B sub 2,000. But the point is it stops somewhere. We don't exactly know how many terms are in the sequence, but we know there's an end to it somewhere. Okay, so for a sequence to be unique, there has to be some kind of formula, as I said earlier, to calculate the terms. Now, there might be more than one formula for the same sequence, but chances are if you come up with a formula for the sequence that I'm showing right here, and somebody else comes up with a formula that looks different, they're probably really the same formula. Because if they're giving you the same sequence, you can probably reduce it a little bit so the formulas would look the same. Now we're going to just start out by looking at sequences and trying to figure out the pattern kind of just by looking at it. For some sequences, there are tricks you can use to figure out the pattern. In general, though, if you just had a sequence and it doesn't fall under one of the special tricks we're going to learn, then it could be pretty hard to figure out the formula. It could be really hard. So the ones that I give you that are not one of the special tricks, they're going to be pretty straightforward. And then if it is one of the special tricks, you just have a formula you can use to find the pattern. All right, so let's look at this one and just see if we can figure out a pattern. It's 2, 5, 8, 11. And this one happens to be an infinite sequence, right, because of the ... at the end. That doesn't really matter. But the point is, I just want to see if we can find a pattern. Generally, to find a pattern, you've got to know the first 3 or 4 terms. If you only know the first 2 terms, like let's say only you knew the 2 and the 5, and that was it. There's a lot of ways to get from 2 to 5. You could say, oh, well, maybe I double it and then add 1. Or maybe I square it and add 1. Or triple it and minus 1. There's all kinds of ways. But then once you get the 2, the 5, the 8, and the 11, that kind of establishes the pattern. So what's the pattern here to get from one term to the next? Yep. Add 3 to what? The term before it. So let's see how we would write the term before it. I know how to write add 3 plus 3. So to get the nth term, you take the 1 before it and add 3. So right here, we want to put the 1 before. Well, I don't want to write that. I want to come up with a way to represent it. Does anyone think they know how you can write the 1 before a sub n? What would be before it? Yep.
A sub n minus 1.
Yeah. A sub n minus 1. So there's a formula that would generate the nth term relying on the 1 before it. Now there's a name for that. Okay, we'll talk about that later on. If a formula relies on the 1 before it, that's one type. Let's see. Let's see if we can come up with a different formula. Okay. What I'm going to do below each number in black is write its position in the sequence. So that's in the first spot, second spot, third spot, fourth spot. Does anyone see what you can do with the position number? Like the 1, the 2, the 3, and the 4 to get the black number above it. There's some arithmetic you can do to 2 and get 5. And then there's the same arithmetic you can do to 3 and get 8. Yep.
Multiply by 3 minus 1.
Yeah. So if you take the position you want to know, multiply it by 3 and minus 1, that's another formula. Let's try it. To get the 1 in the fourth spot, you would plug in a 4. 3 times 4 is 12, minus 1, 11. Works perfect. Let's check the third spot. 3 times 3 is 9, minus 1 is 8. Now, out of these two formulas, which one do you think would be easier to use? The top one or the bottom one? Yep.
The bottom one, because you don't need to know the previous number.
Right, the bottom one, because if you wanted to find the 500th number, all you'd have to do is 3 times 500 is 1500 minus 1, 1499. Done. If you wanted to know the 500th term here, well, let n be 500. So the 500th term is equal to a sub 500 minus 1. So it's equal to 499 plus 3. But the problem with that is you don't know the 499th term. So now you need to find that one. And the 499th term is going to depend on the 498th term and all the way back. So formula in black, you have to know every term up to the one you want to know. The one I put in red, you can find any term directly. Okay? So the one in red is a better formula. A little harder to come up with, but much better. So for a second, I want to think about a function. Okay, so remember, a function is a formula. You plug in a number for x, you get one answer for y. One and only one answer. Well, that's kind of like what this is. This formula right here, if you plug in a number for n, you would get one and only one answer for the specific term you're looking for. But there's a restriction on the n. There's only certain numbers you're allowed to plug in. Since n represents a position in a sequence, what kind of numbers are you allowed to plug in for n?
Integers.
Close. I can think of some integers you can't plug in.
Positive.
Yeah, it has to be positive integers. All right. So that's basically what this is saying right here. If you take any function and restrict the domain of it to just positive integers, 1, 2, 3, 4, 5, you have a formula that could be used to define a sequence. Okay. You can't plug in anything other than positive integers because think about, like, if you have a sequence, you've got a number in the second spot, you've got a number in the third spot. There's nothing between them. Second spot, third spot. It's kind of like in a race. Somebody could finish second, somebody could finish third. There's nobody that finishes in between second and third. You don't finish 2.5. Doesn't make sense. So take a function, restrict it to positive integers for the domain, and you've just created a formula that could represent a sequence. That's all. So two kinds of sequences we can have are an infinite sequence and a finite sequence. Okay, the difference? An infinite sequence, if you think of it in terms of that formula? Well, in an infinite sequence, you can plug in any positive integer for the domain. Anything. Because it goes on forever. With a finite sequence, you cannot plug in any positive integer you want. There's a limit. Maybe your sequence has 10 terms. So that means you could plug in up to 10. You can't plug in 11 because 11 doesn't exist. It stops at 10. So an infinite sequence, the domain for the formula that describes it is all positive integers, versus a finite sequence, the domain would be a subset of the positive integers. The subset would be all numbers from 1 up to something, okay, up to n. Now, when we start to talk about a series, okay, which is when you take all the numbers in a sequence and add them up, you can always find a sum of a finite sequence because it ends. Even if you had a finite sequence with 1,000,000 terms in it, a computer can add up 1,000,000 terms. It can be done. What gets a little bit more interesting is when we try to add up all the numbers in an infinite sequence. Okay? So you're trying to add up an infinite amount of numbers. And can you do that? Depends. Depends on what you're trying to add up. Sometimes you can, sometimes you can't. So we'll talk more on probably Wednesday. Yeah, we'll talk more on Wednesday about adding up all these numbers in an infinite sequence. Tomorrow we'll do it for a finite sequence. Okay, so this one is just having us practice list out terms in a sequence given a formula. And this is the kind of formula that we like to have because it's direct. You can find any term you want without finding the ones before it. Okay, so let's start with the first term. So all we have to do is let n equal the term we want to find and do it out. So let's start with when n is 1. Right, so Shauna, if I plug in 1 for n, what do I get in the numerator?
0.
Yeah, I get 0. It doesn't even really matter what's in the denominator. And I get the first term in this sequence is 0. Okay, Dylan, let's look at the second term. What do I get in the numerator if I plug in 2?
3.
Yep, I get 3. And the denominator is just the term you're looking for, so 2. So the second term in this sequence is 1.5. Gracie, how about the third term? 8. And the denominator?
3.
So we get 8/3. And if we go all the way to the 15th term, what do I get in the numerator if I plug in 15 for n? Yep, 224 over 15. Now, if we look at it, there's a pattern here to what we're getting closer and closer to. Okay. We started off with 0. The next number was 1.5. The next number was 2.6 repeating. 224 divided by 15, 14.9. If you notice, the term itself is getting pretty close to its position number. That's what's basically happening. And the reason for that is when you square a number and then -1, minusing 1 doesn't even really make a difference. Think of like if n was 1,000,000. If you square 1,000,000, well, you square 1,000,000 and subtract 1, big deal. Like subtracting 1 from 1,000,000 squared isn't really that big of a difference. So when n gets huge, that part basically becomes insignificant, and you end up with this. Essentially. Basically, that's what ends up happening. Okay. And then if we divide this out, that formula reduces to n. So it's never going to reach n, but it's going to get very, very, very close to it. Okay. Any questions on that one? All right. Let's look at this one. Okay, a little different. Can anyone describe to me what that -1 to the n is going to cause to happen in our sequence? Yeah.
Is it going to change the sign?
Yep. It's going to change the sign. So this is going to be an alternating sequence, positive, negative, positive, negative. Okay, because we know that any negative number to an odd power is negative, any negative number to an even power, positive. Other than that, other than the alternating, it's going to double each time. Okay, that's what the 2 to the n is going to do. All right, so let's do out the first few terms. Jane, what's -1 and to the first power?
-1.
And then 2 to the first?
2.
2. So the first term in this sequence is -2. Megan, how about if I plug in 2 for n? What would I get for my first factor? 1. And my second factor? 4. So it doubled, but it changed sign. Okay, so we can do out one more. To the third power, -1. 2 cubed is 8. -8. Right, and now to the 15th power. So Leo, is it going to be a positive or a negative?
Negative.
Yep, it's going to be a negative because it's -1 to an odd power, and then 2 to the 15th. That's small enough that we could do it out. Is that what, 32,768. There becomes a point when we don't do it out anymore. Like if it was 2 to the 50th power, that's probably too big. Right, we would just leave it as 2 to the 50th. But if you ever have a question on should I do it out or not do it out, the directions on the test will be clear. Okay. So any questions on that one? So anytime you see a sequence that's alternating positive, negative, positive, negative, if you have to figure out the formula, this is a good place to start. Put in a -1 to the n. Now, what if you wanted to adjust it so instead of starting on a negative, it started on a positive? What would you have to do to adjust for that? Yeah?
Make the exponent n-1.
Yeah, there's actually a couple ways you could do it. You could make the exponent here an n-1. You could make the exponent here an n+1. You could do it either way. So a couple different ways you could do that. You could also combine this into something a little shorter. If you did -2 to the n, I think that would give us the same thing we have right here. -2 to the first is -2. -2 squared is 4, and so on. Right? So if you came up with the formula on the left and someone else came up with the formula on the right, you're both right. But I would say the one on the right in red is a little more simplified than the one on the left. But they're both fine. All right, so earlier we said that when we describe a sequence, it's basically a formula. But the difference is it's a formula where you can only plug in integers for the domain, positive integers. So we can think of graphing a sequence, but you don't want to think of it as being connected. Okay? You want to think of it almost looking something like, in fact, I'll just go back in a second, pick out a formula we already have. Let's look at this one. A sub n equals 3n minus 1. Well, if you were going to graph it, and that was an algebra problem, in algebra it's basically like y equals mx plus b. It's a line with a slope of 3 and a y-intercept of -1. Well, when we draw it, we wouldn't want to do it as a line, okay? Because a line means that you can plug in everything. It's connected. It's continuous. When we draw it, it would look something like this. Let's grab graph So it's got a y-intercept at -1, and the slope is 3. So I can go up 3, right 1. Okay. Up 3, right 1. Now, I'm going to erase that one because that one represented the 0th term. There really is no such thing as the 0th term. You have first, second, third, and so on. But you really don't have anything before it. But when I graph a line, I like to start with the y-intercept, so that kind of helped me to do it. But that's up to you. And then up 3, right 1, and then we keep going. And that would be the graph of the sequence. You don't connect it, because there's nothing in between 1 and 2. It's a jump. Okay. So let's try the same thing with the formula we just had before. A sub n equals n squared minus 1 over n. Now, I'm only going to graph the first 3 terms, okay, because this gets pretty big. I think the 15th term was almost 15, and that's going to go off my grid. All right, so when we did this out, what was our first term? What did that come out to? Yeah? 0. So the first term is 0. Not the 0th term is 0. The first term is 0. Okay, so think of it like this. First term, 0. Second term. Okay, what did our second term come out to? Yeah. 3 halves. So for graphing purposes, decimal is a little easier. So second term, 1.5. And you might be tempted at this point to think it's a line. It's kind of a line, but that's not the equation of a line. That's not y equals mx plus b. It's going to kind of look like a line, but if we could draw it really accurately, it wouldn't be a perfect line. Okay? Because of that. All right, let's see, the next one, the third term. What was the third term again? That was what, 8/3, so that's 2 2/3. So 2, and then it's kind of the best we can, 2/3. So what's going to happen as we're going, each time I put another dot, it's going to get closer and closer to the horizontal line that's the next one above it. It's going to get closer and closer to it. So by the time you get all the way out to 10, that would be 99 divided by 10, 9.9. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's going to be up at 9.9. And you could fill it in between if you want to. But that's the idea of how you graph a sequence. Just don't connect it. Okay, questions on that? All right, so the formula that I gave you right here, and the one I gave you right here, these are called explicit formulas. Explicit formulas are the ones we like to use, okay, because what they allow you to do is calculate any term you want to know directly. Kind of the opposite, or kind of the flip side of an explicit formula is a recursive formula. In general, when people look for patterns, this is how most people see it. They see a recursive pattern, meaning they say, oh, the next number is just the one before it plus 3. Well, that's easier to think of, but it's not easier to work with mathematically. Okay, so in a recursive formula, what I have to do is give you the first few terms. And that's important, because if you don't have the first few terms, and I just say to you, okay, I'm thinking of a sequence, and in my sequence, to get the next number, you add 5 to the one before it. Well, if you don't know where to start, then you can't figure out anything. So if I said to you, okay, the first term is 1, and then to get the next one, you add 5 to the term before. Well, now you could say, okay, the second term is 6. Okay, so in a recursive formula, they'll always tell you where to start. And to find the term you want to know, it's going to depend on using the previous terms. Now, notice I put in parentheses here. Could be previous term, like in the formula, add 3 to the one before it. or it could be previous terms. And that's where things can get really hard. Like if I gave you a formula like this, let's say I said to you to get the nth term, you do triple the one that's 2 before it, and then you add double the one directly before it. That could be a pretty tricky one to come up with. And what would be even harder would be to convert this into something like that. That can be very, very difficult. In fact, there was a class I was in at one point, and we practiced doing that, and it's pretty hard because it involves some guesswork sometimes. Like sometimes you've done a lot of these, you kind of know like a pattern, but sometimes you have to kind of take a guess and try something. It takes about 5 minutes to try it. And then if you get to the end and you get a certain result, you're like, wait a minute, it didn't work. Then you got to go back and try something else. So it can be pretty hard to do stuff like that. But if I give you anything that's recursive, it's going to be pretty easy to turn it into explicit by hand because I'm not teaching you the method to do it. So here's one that's a little easier. And it just says the first term is 2. And to get the next term, take 3 plus the one before it. Okay. So in this case, how about Juliette? What would my second term be? So the first term is 2. And then this formula, actually, can someone tell me what does this formula mean? 3 plus a sub n minus 1? If you wanted to kind of translate that into something regular people can understand and not math geniuses. Yeah?
Adding 3 to the term before it.
Yeah. So it takes 3 plus the term before it. So if you want to know the second term, it's 3 plus the one before the second term, which is 2. So in this case, the second term would be 5. Yeah. And now if you want to know the third term, you take 3 plus the term before it. So now we've got 3 plus the term before it is 5. So my third term is 8. And again, if you're doing this recursively, you could easily make a mistake. Say you want the 200th term. Well, if you just keep adding 3 each time, you might make a mistake doing that. So we gotta get a better way to do that. And we will. But any questions on how to evaluate, or not evaluate, list the terms in a recursive sequence? Okay, so here's another one. Determine the first 4 terms and the 8th term of this. So the first term is 2, and the nth term is 4 plus the term before it. So a lot of times what I do is I just make a table where one row represents the position and above it is the term. So Tessa, what's my first term here? Two? How'd you calculate that? It says it. She didn't calculate it. It's given. Right? So the first term is 2. They always got to start you off somewhere. And now we follow the rule from this point forward. 4 plus the term before it. So Rebecca, what's my second term? 6. Caleb, my third term? 10. And well, Tanya, my fourth term? 14. Now, we found the first 4 terms, and they want the 8th term. But really, if we're following the formula to get to the 8th term, we have to find the 5th, 6th, and 7th, even though they don't want that. So 18 is plus 4, 22 plus 4 again, 26. Now I finally have the term before the one I want, so now I can get the 8th term, which is 30. Yeah?
Couldn't you just say, so you're starting with the first position, and for the 8th position, that's going up 7 spots.
Mm-hmm.
And if you're going up 7 times, couldn't you just say you're going up 28?
Yeah. So eventually we're going to kind of turn this into an explicit formula that uses multiplication. That's basically what this would do. Because if you're going to repeatedly add the same number over and over and over, well, in like 2nd grade, you learn that adding the same number and over and over and over is just multiplication. So we can shorten this up with multiplying. Yep. And we're going to do that. So any questions on that? All right. Okay, so here's one. We're going to try to do what we just said. But I'm not going to show you a formula to do it. I just want you to try to figure it out, just thinking it through on your own. But there is a method, kind of a procedure to follow to do this if you can't figure it out just by guessing, basically. All right, so here's the recursive sequence. The first term is 3. The nth term is 5 plus the term before it. And what I like to do is just list out the first couple terms. Okay, that'll kind of help you to see the pattern. So Dylan, what's the second term here?
8.
8. And the third term?
13.
13. All right. So now what we want to do is think of some kind of arithmetic we can do with a 2 to make it an 8. And the same arithmetic we can do with a 3 to turn it into a 13. And it's going to have something to do with the number you've added over and over, which we said is multiplication. Yep.
Multiply by 5 minus 2.
Yeah. So the nth term can be calculated the way they told us, or a better way to do it is to take the position you want to know, times 5 minus 2. 3 times 5 is 15, minus 2 is 13. Just because it works in one spot, that doesn't mean it's going to work all the time. So double check. First term, 1 times 5 is 5, minus 2 is 3. 2 times 5 is 10. 2 times 5 is 10, minus 2 is 8. Now, there could even be some sequences that get really tricky where you check it here, here, and here, and it works. And then the fourth one, it doesn't. That's pretty rare, but it could happen. But I'm positive we do have the correct formula here. Okay, and after I show you kind of the procedure you can go through to get this formula, very mechanical, we'll come back and see if we get the same result, okay, doing it with a procedure, okay, rather than just kind of guessing. All right. Any questions on that one? All right, so there's our formula. All right, so the next pattern we're going to look at is probably one you might have heard of before. Anyone heard of that before, the Fibonacci sequence? Anybody know what it is already? Like how you get from one term to the next in the Fibonacci sequence? Yeah?
You add the previous 2 numbers together.
Yeah, you take the previous 2 numbers and add them together. So since he just said that this formula relies not only on the term before it, but the one before that, I have to start you off with the first 2 terms. So the first term is 1, the second term is 1, and the nth term is the sum of the 2 before it. Now, really, a Fibonacci sequence falls under a broader category called a Lucas sequence. And a Lucas sequence is where you just take the 2 numbers before, add them together. What makes it a Fibonacci sequence is you start off with a 1 and a 1. In general, this is a very hard formula to convert to explicit. So like if I said to you, what's the 1000th term in the Fibonacci sequence? I don't think there's anyone in here that's going to get that in under 5 minutes. Probably even under a half hour. Okay, or an hour. It's going to take a long time to get the 1000th term. There is a way to find a formula that will do it, but it's way, way beyond pre-calculus. So we're just going to stick with trying to do it this way, and we're going to just do a reasonable amount of terms, the first 6. All right. So we already have the first and the second term. Okay, what would my third term be? Yep,
2.
2. And the fourth term?
3.
3.
5.
Yep, and then 2 plus 3 gives me 5, and then now 3 and 5 gives me 8, and 8 and 5 gives me 13. Okay, have we listed how many they want? 6? We did 7. That's fine. Okay, so that's a Fibonacci sequence. And there's all kinds of patterns and stuff you could study in that sequence. Okay, but that's all we're really gonna do with it. Okay, any questions on that one? All right. So this is a special triangle. Does anybody know the name of this triangle? It's kind of like the Fibonacci sequence, right? Because you take the two numbers above it, you add them together, and that gives you the one below it. But does anyone know the name? It begins with a P. There's an old computer programming language named after this. Yeah?
Python?
Not Python, Pascal. Pascal's triangle. So Pascal, that was a good guess. This is Pascal's triangle. This comes up a lot in section 11.3. It's used with probability, but it makes kind of a weird appearance here too with the Fibonacci sequence. The Fibonacci sequence is kind of hidden in that triangle. And unless you're really good at patterns, without giving you a hint, I don't think you'll see where it is, but those lines kind of give you a huge hint off to the side. Yeah?
Well, I know because Bab showed it to me, but if you take the 2 above it, so like for row 1 going into row 2, it makes a triangle, so you take like, it's hard to explain without like pointing to it, but like row 1 is like the 1 and 1, so row 2 has like the 1 plus 0 above it is 1, and then the 1 plus 1 is 2, and then it's hard to explain. I know. Like when you like write it out, it's easier to explain than just having it up there.
To see it? Yeah, well, let me show you, because I can show it kind of pretty easy up here with these lines. If you put these lines in it, just like that. Okay. Does anybody see the Fibonacci sequence now? If not, I'll say one more word and then see if you see it. Add. That's my one more word. Add. Anyone see it now? No? Do you see it, Jane? No?
Well, I saw it before.
Yeah.
You saw it before?
Yeah, I don't really know what the lines represent.
So, actually, there's a couple ways I can put these lines. Let's, I could do it that way too. That's probably even better. So, look at the first line in red, and then add up all the hexagons, I guess, that it goes right through. So, if you add up all the hexagons that the first line in red goes through, what do you get? 1. Okay, now let's do the same thing for the second one. Look at the second red line and add up all the hexagons in red, all the hexagons that the red line goes right through the middle of. What do you get there? 1. Okay, now do it for the third line. A 1 and a 1. 2. Do it for the third one. 1, whoops, I skipped 1. 1 plus 2 gives me 3. Now do it for the fourth one. It goes through the 1, it goes through the 3, and it goes through the 1. 1 plus 3 plus 1, 5. And you could keep going. But the point is, if you add up all the numbers on those diagonals where the red line goes right through the middle of the hexagon, not on the boundary, but right through the middle of it, like 1, 4, and 3, that will give you your next number. 1 plus 4 plus 3 is 8. So Pascal's triangle, there's a ton of stuff that happens here. Another important thing that it tells you that you'll see in 11.3 is how to do what we call combinations with objects. Like if I had, say, 4 objects and I wanted to know how many ways I could pick 2 out of the 4. I could pick the black and the blue, I could pick the blue and the green, I could pick the green and the black. There's all different combinations of ways you can do it. And this chart basically tells you that. But that's something you'll look more at when you look at 11.3. But for now, I just wanted to show you that if you just add those diagonals up, the Fibonacci sequence kind of pops out of that. What would be really difficult is proving why. Why does that happen? That's a little deeper question. Right, so there's 2 main sequences that we study, and you've already seen some examples of today. One is called an arithmetic sequence, or progression, same idea. And the other one is called a geometric sequence, or progression. So with an arithmetic sequence, basically what you're doing is you are adding a number over and over. So it says here, a sequence is arithmetic if there is some number such that this ends up happening. To get the nth term, you take the one before it and add d. And the reason we call it d is because d is the common difference of the sequence. Now, at first, that can be a little confusing because it's saying right here, well, you're adding d each time. So if you're adding something, why do they call it a difference? And I'll show you that in a second. Remember, adding and subtracting is basically the same thing, right? So subtracting is just adding negatives. So the reason they call it a common difference is because, let's say you had the following sequence. 2, 5, 8. What I'm doing is I'm adding 3 each time. Plus 3, plus 3, plus 3. Well, take any 2 numbers that are next to each other and subtract them. The one on the right minus the one on the left. 5 minus 2 is 3. 11 minus 8, 3. 17 minus 14, 3. So the common difference in that sequence is 3. And that's one of the 2 numbers that if you can find it, you can figure out the pattern. So you need to know the common difference. And the only other thing you need to know is the first thing. If you tell me those 2 things, I can write a formula by doing this. So now this gives you a way to write an explicit formula for an arithmetic sequence without guessing. It's not like, well, is it 5 times that minus 2 or 3 times it minus 7? This tells you exactly how to do it. It's the first term plus n minus 1 times d. Now earlier we had an arithmetic sequence and I just said to somebody, like, what do you have to do? What kind of arithmetic would you have to do? And someone was just able to figure it out. Again, the process they used, I can't really explain what was going on in their head, but they figured it out. Maybe they just guessed and it worked. This is not a guess. It gives you a method to follow. So let's go back to that formula we just did and try this and see if it works. Okay, remember the restriction on n, positive integers. Okay, so it's the first term plus n minus 1 d. So let's go back right here. So we somehow we figured that out, but let's try our other formula. It's the first term plus n minus 1. And what's the common difference between these numbers? Okay, 5. Okay, so now if you look at the result in black and the one in red, you might be like, wait, they're not the same. Well, if you simplify it, they will be. So distribute 3 plus 5n minus 5. And now 3 minus 5 gives me a negative 2. And there's exactly the same formula we just got in red without really any guessing involved. Okay. Unfortunately, that only works for an arithmetic sequence. Like, this is not arithmetic. 1 minus 1 is 0. 2 minus 1 is 1. 8 minus 5 is 3. That formula is not going to work for this because there is no common difference. Okay, so let's try this one. Now there'd be one problem with this. If I asked you to find an explicit formula for this on the test, you couldn't do it. How come? Yeah.
Because you don't give us the first term.
Yeah, I don't give you the first term, so I gotta give you that. Can let the first term be whatever we want. 2. So now we know the first term, and we know how to get each successive term. What's the common difference going to be? If you're not sure, you could write out the first few terms, but after a while, you should be able to just look at it and say, oh yeah, it's written right there for me. 3. Common difference is 3. First term is 2. So unsimplified, can someone just tell me what the formula would be for the nth term?
2 plus, in parentheses, n minus 1 times 3.
Times 3. Okay, we always want to simplify that up, okay, as much as you can, so always distribute it. So we get 2 plus 3n minus 3, and then combine your like terms. What I like to do is now list out a few terms and make sure that it does work. So the first term was 2, and then the next one is plus 3. So 5, 8, and so on. Now let's check our formula and see if it works. To get the fourth term, 3 times 4 is 12, minus 1 is 11. Yep. Third term, 3 times 3 is 9, minus 1 is 8. It seems to work fine. So any questions on how to take a recursive arithmetic sequence and convert it to explicit using our formula? So that's for arithmetic. Let's see if we can apply kind of an idea here. I want to find the fifth term, and they're giving me the first 2. Well, I know we could probably do this by hand, but let's just practice finding the formula. What's the common difference here? Yeah.
6.
6. So the common difference is 6. First term is negative 8. So my formula, first term plus n minus 1 times the common difference. So we're going to get 6n minus 6 combined with a minus 8. So there's the formula. And you can check it. If you plug in 2, 6 times 2 is 12. 12 take away 14, negative 2. So I want to check it for another one, but it does seem pretty good. All right. So now to find the fifth term. 6 times 5 is 30. 30 minus 14 gives me, 16. So there's your fifth term. Questions on that one? Let's try one different. So here they want a formula for the arithmetic sequence, but you're missing the first term and the common difference, but they've given you enough information, you should be able to find it. How could you figure out what the first term is here? What could you do? Yeah.
Well, I don't know if this is what you were thinking, but to go from the 3rd to the 8th spot, you're moving 5 spots.
Yep, you make 5 jumps.
And the number changes by 10.
And it changes by 10.
So if you do the 10 divided by 5, You get 2.
You get 2, yeah. So to go in an arithmetic sequence, you got to do the same thing each time, and it has to be addition or subtraction. In this case, it's clearly subtraction as you move to the right. And as Jan just reasoned it through, you're going down 10 units in 5 intervals. So to do it equally, it's 2 units down per interval. So now to work backwards and get the first term, what would you do from there?
You would add 2.
You would add 2. So 15, there's your first term. Now they didn't ask for that, but to find the formula, that's part of it. So my first term is 17. Common difference. What's the common difference here? Yeah?
2.
Be careful.
-2.
-2. It's always term minus the 1 before it. So common difference is -2. All right, so my formula, -2 plus n minus 1 times the common difference. I messed that up. So first term plus n minus 1 times the common difference. Sorry about that. So now we get 17 minus 2n plus 2, which is going to give me -2n plus 19. Okay, so any questions on working with arithmetic sequences? Okay, so last type we're going to look at is geometric. Does anybody remember from Algebra 2 what a geometric sequence is? Yeah?
It's it either multiplies or divides.
Yeah. And what is that called when you repeatedly, well, when you repeatedly add the same thing, we call it multiplication. But what about when you repeatedly multiply by the same thing? What's a shorter way to do that?
Exponential.
Yeah, exponents. So this geometric formulas are going to involve exponential expressions. Right? So we'll have variables in the exponents. So geometric is to get the next term, you multiply the previous term by a constant. So instead of adding to the previous term, you're just going to multiply the previous term. So that would be the formula for a recursive way to write a geometric sequence. Take r, which is some number they would give you, times the term before it. R is what you're multiplying each time by, and that's called the common ratio. So a geometric sequence doesn't have a common difference, it has a common ratio. So if you look at this pattern, 3, 6, 12, 24, 48, what am I doing each time? Yeah, and if you take a term and divide by the one before it, that's the pattern. 48 divided by 24, 2. 12 divided by 6, 2. So that's how you find r. Take a term and divide by the one before it. Or take the term after and divide by the one before. It's same thing. Take a later term, divide by an earlier term. And that's the explicit formula for a geometric sequence. So notice exactly what Caleb had mentioned. It's going to exponent. And you have to multiply the first term by r n minus 1 times. So if you wanted to get to the 5th term, you would have multiplied by something. Just kind of think it through. You would have multiplied 1, 2, 3. You would have multiplied 4 times to get to the 5th term. That's why there's a minus 1 here. Okay, so let's look at an example with a geometric sequence and see what happens there. Okay, so it says find an explicit formula for the geometric sequence. Now, this time, it's kind of like the one where I had a table with arithmetic, but I put the two terms next to each other, so it's a little easier. Now, remember, you're thinking geometric. So don't say, oh, you added 18. No, that's not the pattern here because they said geometric. What's the common ratio here? Yep. Yeah, you're multiplying by -2. So if you were to continue, but what's more important is we need to work back and get the first term. What's the first term going to be? Yep, 3. So now I've got the first term, and I've got my common ratio is -2. So the first term times r to the n minus 1. First term times r to the n minus 1. Let's try it for the third term. We should get 12. 3 minus 1 is 2. -2 squared is 4. 4 times 3, 12. Perfect. Okay, so geometric formulas are going to involve exponential expressions. Arithmetic formulas are going to involve multiplying. Okay, so any questions on arithmetic or geometric sequences? Okay, so that finishes up 11.1. Okay, tomorrow we'll look at, tomorrow and Wednesday we're going to look at series, which is adding up all the numbers in a sequence. See if we can find some formulas to do that stuff a little quicker as well. Okay, so homework, it's all odds except for 14. So 1 through 7, 9 through 13. 14 is the only even. 17 to 27, and 31. And all odds except for 14.